I am very, very happy to have the opportunity to introduce our speakers from VeruTEK Technologies. Our speaker is Dan Socci, who is the CEO of VeruTEK. And in his biography, he tells us that he leads the company's effort to capitalize on strong market demand for its innovative technology while further extending its intellectual project and product portfolio. Dan has over 20 years of experience in the information technology industry, most recently in a vice president position at Hewlett-Packard. And I'm sure that many of you know that Hewlett-Packard has really taken the lead in really trying to incorporate the principles of green chemistry into its product line. We had a presentation by Helen Holder, and Hewlett-Packard is known for taking a leadership role in the BizNGO network and in using the green screen. So we know that Dan comes from a very progressive company. And while he was at HP, he was a member of the leadership team for the $9 billion Technology Services Division, and he was responsible for the development and implementation of a number of initiatives to increase revenue, profits, and customer satisfaction. So early in his career, he also had management responsibility at Compact Computer Europe, Middle East and Africa region sales and marketing, as well as management roles with Digital Equipment Corporation headquarters. And Bethany McAvoy is the technology manager for VeruTEK, and she utilizes her background in biology and chemistry to communicate scientific research and concepts internally to sales and marketing and externally to outside business and clients. She leads product management by conducting market research work to determine new areas for VeruTEK R&D and third-party testing, characterization of new products. And I think that, hope you'll all take advantage of this opportunity to really ask her questions or make comments on your own ideas for new areas for VeruTEK R&D. So with that introduction, I'm going to turn it over to Dan and Bethany and listen to the webinar.
Great, Lynn. Thanks very much for that wonderful introduction, and thanks for the opportunity to present today. Clinton, thanks also. And we're very excited to be here and have the opportunity to take you through the agenda that we have up. We'll tell you a little bit about the company, give you a background on who we are, what we do, and we'll spend most of our time with Beth McAvoy taking you through the technology, which we think is innovative and a real step forward in green chemistry. And as Lynn said, a proof point of a technology coming out of the lab and into the field, and we'll share some of that field experience with you. So VeruTEK develops high-performing solutions based on green chemistry for 3 applications. So we work on environmental remediation in the subsurface, destroying toxins through green chemistry. We also do surface cleanup applications, particularly for cleaning up oil spills and removing PCBs. And then we also have a related business, which is based on the same chemistry platform, enhanced oil recovery, where we improve the performance of aging oil wells. We are a technology company, as we said. We focus on developing new and innovative solutions. We did have our first 3 patents issued in 2011, and we have another, 16, it's actually 17 now, patents pending. And our focus in the chemistry arena is on taking plant-based chemistry, combining those to produce unique chemical oxidation solutions. And we think that we are highly differentiated from traditional chemical oxidation in the environmental remediation segment. So those of you who might be familiar with chemical oxidation, we think we do have some advances there that are unique and really change both the implementation and maybe more importantly the results from chemical oxidation. So we'll be covering that shortly. Some of the highlights on what the solution allows people to do is to achieve source destruction, and that is very different for a chemistry solution to remediation. It presents for the first time an alternative to excavation by allowing you to use the chemistry both to destroy the source of the contamination and then also to get to places that are hard to reach for excavation. So these would be understructures and where there might be utilities in the underground. So those are obstacles in addition to depth of contamination that also presents a problem for excavation. So people are very interested in having that kind of an alternative. Another differentiator is that our chemistry would operate in a relatively short time frame. And this is both in terms of requiring fewer injections, as you'll hear from Beth, by destroying the source of the contamination. That is a very different outcome, so the chemical treatments do not have to occur over a long period of time, multiple treatments. And then also there is an approach using bioremediation, which operates on a much different time frame, oftentimes taking the course of years to achieve source destruction. So for a timely, cost-effective, with a predictable outcome source destruction, we think that this technology is unique. And lastly, it is a permanent solution. So the source is destroyed, it's taken out of the soil, and this allows us to achieve a result that does not have rebound. This is a common problem with chemical oxidation, that it's only a partial solution for the near term after the treatment, and then the groundwater contamination occurs again. So we found ours to be a permanent solution. It's a solution that has been implemented on over 40 sites, so we are very much out of the lab and field proven. Sites of a broad range of sizes. Some have been multi-million-dollar, multi-acre properties that we've remediated. We also do supply the chemistry to smaller implementers. This is a change that we made in 2010 as the technology matured to outlet it through a number of new partners, and they've taken us out to many different places, different shapes and sizes of sites, as well as the contaminants that you see here. So we do address the organic contaminants, so we won't be talking today about the inorganics, the metals. The focus is on organic contamination, as you see it here, essentially the hydrocarbons of a wide range of types and the chlorinated solvents. We do work with a number of partners, so we do have a group of scientists here who develop new solutions, but we also take advantage of resources at Yale University, the University of Connecticut, and then we also have worked with the Electric Power Research Institute doing a test there in Pennsylvania earlier this year, which will both get us excellent feedback on the technology as well as visibility. We work primarily in the U.S., but we have done projects internationally, Australia and Denmark. We worked with Australia's CRC Care, which is the nation's largest and leading consortium of industry and government to drive environmental cleanup. On the oil recovery side, we work with University of Wyoming and Kansas University. And then, as I said, we did two projects in Denmark and worked with the University of Copenhagen. We also work with EPA. We've done a number of things there, and we are visible to a number of branches of EPA. One of our patents, I mentioned we had 3 issued in 2011. One of them, we received a notice in late 2010 on our green zero-valent iron product, and that was jointly developed with EPA. We did get a surface washing agent listing. Beth will talk a little bit about that later in December 2010. And we have been addressing Superfund sites, most recently a site in Delaware, which was EPA federally and state funded. So that's a little bit about the company, and now I'm going to turn it over to our technology manager, Beth McAvoy, to take you into the chemistry.
We're mostly going to focus on our surfactant-enhanced in-situ chemical oxidation technology. This technology is really a platform that's allowed us to address the multiple applications that Dan discussed. This chemistry platform has some green components to it. The surfactants that we're using are biodegradable. We've done testing to determine how long they're going to survive in soils and to make sure that's limited. They're very low toxicity. We did an extensive amount of toxicity testing as part of our efforts to get on the EPA surface washing agent list. And all of the surfactants are plant-based. They're not synthetic. As Dan mentioned, we co-patented a new green synthesis technique with the EPA, which uses polyphenol-rich plant materials such as green teas, sorghum. You could even use waste products from wine manufacturing or olive manufacturing to form these nano-iron catalysts. And we believe our in-situ treatments are a lower carbon footprint solution to a lot of brownfield development projects compared to excavation because of the less amount of equipment used and the fact that we're not moving the contamination to a landfill, we're actually destroying it in place. So surfactant-enhanced in-situ chemical oxidation uses these plant-based biodegradable surfactants with a catalyzed oxidant to destroy contamination that's in the soil and stored tightly to the soil and contamination that's in the groundwater. These two components of our chemistry are stable together. The surfactant helps stabilize the oxidant and actually improves the treatment performance. I'm going to go through on a molecular level how this chemistry is working in the ground. This illustration represents contamination, which are drawn with these black ovals tightly sorbed to a soil particle. Contaminants can form very tight complexes with soil, especially hydrophobic contaminants. They can sorb into inner sphere complexes and nanopores and be very difficult to remove from soil. In addition, water molecules, which in this diagram are represented by the blue structures, can create another barrier to access these contaminants because they're actually forming a cage around these bonds with the contaminants in the soil. Our chemistry, once it enters the system, will self-assemble into structures known as micelles. A micelle is a circular structure represented here with the yellow surfactant molecules. These micelles are actually capable of carrying our chemistry and the catalyzed oxidants into the subsurface where they can deliver it to the contaminant. Part of the surfactant molecule likes water and part of the surfactant molecule is attracted to oils. This makes them a great molecule for overcoming the cage of water molecules around the contaminants and attracting the contaminants off of their bonds with the soil and into the phase where the oxidant can destroy them. So they'll actually desorb the contamination from the soil so that it can be destroyed in place. The end result of this process is just carbon dioxide, water, and the surfactant will biodegrade. This process allows us to access much more contamination than you'd be able to access with a simple in-situ chemical oxidation process. This chart represents a lab study where we put some contaminated soil in a jar with some in-situ chemical oxidation chemistry and then with our chemistry. And what we found is with our chemistry, we were able to bring out much more contamination from the soil, 14,000 milligrams per liter of, in this case, total petroleum hydrocarbons, as compared to 57 milligrams per liter of in-situ chemical oxidation. So the surfactants and oxidants in the Cisco system are working together. The surfactant controls the rate of the oxidation reaction and allows the oxidant to travel in the subsurface without reacting prematurely with things like metals in the soil. So it's protecting the oxidant to extend the life and improve its distribution in the soil. Because we're using the oxidant more efficiently, we're able to use lower doses than you would use in an ISCO treatment. And because you're using lower dosing, it's a safer process, it's less exothermic, and you're improving your dosing and reducing your cost. This is another illustration to show the Cisco process. As I described previously, contamination can be very tightly sorbed to the soil matrix, and it can be trapped in these nanopores where it's very hard to extract. And it also slowly leaches out into the aqueous phase, into the groundwater. Our chemistry can address the contamination that's in the nanopores as well as contamination sorbed to soil and leached out into the aqueous phase. By contrast, traditional in-situ chemical oxidation can really only address the contamination in the aqueous phase of the groundwater, And so contamination that's absorbed to the soil will continue to leach out into the groundwater over time. So what you generally see with these treatments is that you'll go in, clean out the groundwater, and then you'll have to repeat the treatment as more contamination leaches out from the soil. So one of the questions that we often get with this technology is, are you going to mobilize contaminants if you're desorbing them from the soil? But as you saw with our molecular level explanation, the oxidant is right there behind the surfactant to destroy any contaminant that's desorbed from the soil. So if the surfactant is there to detach the contamination from the soil, the oxidant's right there with it to destroy it in place. And we've done a lot of work with dosing to try to optimize this so we avoid mobilization. If we want to detach an oil so that we can collect it so that it can be reused, we can use a process known as SEPR, Surfactant Enhanced Product Recovery, to actually detach the oil, push it towards wells, and recover it. So this is using very different doses than we use during the Cisco process. We dose our studies based on our past experience, our treatability work, and monitoring. Another common question is, what were the byproducts involved in this process? Are there any toxic intermediaries generated? The varicol surfactants are biodegradable, so they break down. We've done testing with that. They're generally regarded as safe by the US FDA, meaning they can be used in food processing and come in contact with food because they're safe. The other components, the oxidants, depending on which oxidants we use, if we use hydrogen peroxide, they'll break down to different gases like CO2 and oxygen. If we use sodium persulfate, you'll get some salt as a residual. The contaminants, many organic contaminants break down to fatty acids. Some will completely mineralize to CO2. If we're not certain what will happen when an oxidant or when it's oxidized, we'll look into the literature and then we'll run studies in our own lab to see what are, if any, intermediary products come up during the oxidation process to ensure that doesn't happen. We work with a lot of major environmental consultants to implement our technology. We work through a few different models. We can sell them chemistry directly. We can do a full implementation. And we can do some work to advise them and give technical support.
Yeah, this is Dan. I'm just going to take you through some comments on the case study. So the first one is a MGP, which is a manufactured gas plant site. So the contaminant there would be a very heavy hydrocarbon. And I won't take you through any of the details on the left, but we'll be glad to answer questions there if you have them. But essentially, the table tells the story. So we were pleased that the chemistry was able to meet the 4 criteria of the destruction per the categories there, total PAHs and so forth. And the attainment was a minimum of 96% up to 100% contaminant destruction. So this gets back to a point I made earlier about our objective with the chemistry is source destruction of the contamination. This one is also a manufactured gas plant site, again, a very heavy hydrocarbon. This one is, happens to be near us here in the Hartford area, and this was a site not far from a river, so making sure that the contamination, as Beth pointed out, was not going to be mobile was an important consideration here. This treatment was both above and below the surface. So this was in situ with injections, and then also ex situ using the device that's shown here in the lower left, a pug mill to mix the soil with the chemistry, different approach. And in this case, the folks were, there's a lower cost where you can do this, where you don't have contamination at depth. This is a good way to treat shallower contamination, and it also gives people flexibility on the outcome of what they'd like to do with the soil, in some cases relocated to another area. So it's the first step in the relocation process. Next one is a site in Texas. This was done through one of our partners, so this is an example where we supplied the chemistry. We did not have anyone from VeruTEK go to this site, but this was a successful remediation. You see the results on the tech side on the left, the lower area under results, 99% destruction of TPH TPH and VeruTEK's contamination. This also gives you a feel on the visual here of the what it looks like. On the left, you have the contaminated soil, the heavy hydrocarbon of obvious appearance there, the black, and then the much cleaner soil over on the right side. So in summary, Beth, did you want me to take this, or you're taking this one?
Oh, go ahead.
All right. So what we've tried to communicate today is that we've got new technology, a new application of green chemistry that desorbs contamination out of the soil. It is unique in having that property, and therefore, once the contamination is desorbed and it's in the saturated zone, below gradient environment, it is relatively easy to destroy with a traditional chemical oxidation. So it's the combination of the new plant-based chemistry desorption with traditional chemical oxidation types of destruction. It is a good solution for relatively permeable soils. This is not a solution for clays, and also it is for the organics, as we said earlier. So we're not addressing any of the inorganic or metal contaminations. There is flexibility both in terms of it being a chemical oxidation process, but also a relatively low dosing of chemical oxidation that it is applicable under structures and utilities. So there are no issues with vapor buildup or corrosion of metals or other things associated with utilities in the subsurface. And the process can be delivered to considerable depth. So we talk about it being delivered above 20 feet. That reference is more about cost effectiveness. So the cost effectiveness really starts to become attractive at around 20 feet. But we do deal with contaminants that are much lower than that. We've done below 50 feet as well. So depth is really not an issue. The wells are relatively easy to get into the subsurface and deliver the chemistry. So ultimately, we've got a great solution for dealing with the soluble organic contaminants of the hydrocarbons and the chlorinated solvents. So that's everything we had for slides, and we'd be happy to field questions.